Let's continue with our discussion on the stoichiometry and energetics. We have learned to use the half-reaction approach to describe the stoichiometry of the biochemical equations for biomass growth, to calculate the delta G for the energy equation Re, and to find the relationship between the fraction of energy flow and the true growth yield. In this class, we will connect the stoichiometry, or yield, with the energetics of the reactions. The thermodynamic electron equivalent model, or TEAM, developed by McCarty et al., helped us relate the energetics with stoichiometry. Because almost all the energy generated from electron donor is spent on growth when the substrate is not the limiting factor. The fraction of electron goes to cell synthesis, or the yield, is determined by the thermodynamics, or the change of free energy, and is also determined by the energy transfer efficiency, as each transfer of energy comes with some energy loss. Here we look at a simple situation where ammonia is a nitrogen source, so there is no change of oxidation state or energy in a nitrogen source during cell synthesis. As you recall, in the energy reaction Re, a fraction of electron donor creates energy carriers, such as ATP, which is then used to drive cell synthesis from the other fraction of the electron donors. If we look at the thermodynamics of the RS reaction, to synthesize cell biomass, the electron donor is first converted to a common intermediate, acetyl-CoA. The energy transfer of this step is delta Gp, which is the difference between the free energy of acetyl-CoA, delta Gc, and that of energy donor, delta Gc prime, which can be looked up in Appendix A in the RM book. Then, driven by the ATP generated in the Re reaction, acetyl-CoA is used to synthesize cells. The free energy change for this process is known for a given nitrogen source. Since ammonia is the nitrogen source in our example, delta Gpc equals 18.8 kJ per electron equivalent of cells. Delta Gs is the overall energy required to synthesize one equivalent of cells and can be calculated from delta Gp and delta Gpc, as well as the energy transfer efficiency, epsilon. The power of epsilon for delta Gp, N, is determined by the relationship of the free energy between the electron donor and the acetyl-CoA. If the energy is generated when electron donor is converted to acetyl-CoA, N equals to -1. Otherwise, N equals to 1. We looked at the energy transfer for cell synthesis. We can now switch our perspective to the energy reaction, Re, and the energy generation from electron donor degradation, delta Gr. We can define that A equivalent of electron donor is needed to synthesize one equivalent of cells. Because all the energy is used for cell synthesis, we can write this energy balance. Energy released from A equivalent of the electron donor equals to energy consumed to synthesize one equivalent of cells. A epsilon delta Gr is the energy generated from electron donor to synthesize one equivalent of cells. And delta Gs is the energy used to synthesize one equivalent of cells. We can then solve for A. A is related to the fractions. In the energy reaction Re, A equivalent of electron donor is consumed to generate energy, while in synthesis reaction Rs, one equivalent of electron donor is used to synthesize cell biomass. According to this, we can find Fs, the fraction of electron goes to synthesize cells, to be 1/1 plus A. This is also true yield, as ammonia is the nitrogen source. And Fe, the fraction of electron goes to electron acceptor to generate energy is A over 1 plus A. Compared to other oxidized nitrogen like nitrates, microorganisms prefer to use ammonia as the nitrogen source for cell synthesis because it is already in the -3 oxidation state. But when ammonia is not available, other nitrogen species available will be used for cell synthesis after being reduced to a -3 oxidation state. When oxidized nitrogen is used as the nitrogen source, delta Gp stays unchanged as the nitrogen source does not participate in this step. Delta Gpc, on the other hand, depends on the nitrogen source. If the nitrogen source have a higher oxidation state, delta Gpc will be lower. The rest of the calculation for A and Fs stay the same. Knowing how the stoichiometry and yield can be calculated from the energetics, let's recall the reaction for the aerobic degradation of glucose balanced in COD. We can calculate the yield based on the free energy change and energy transfer efficiency. We can also write a more general expression. And this is the general expression for aerobic heterotrophs using organic carbon as electron donor, which is the most typical reaction in wastewater treatment. SS is the organic substrate concentration. SO is the dissolved oxygen concentration, and XBH is the concentration of active heterotrophic biomass. And YH is the true yield of the heterotrophs. We can write it in the form of COD balance and transform it by dividing both sides by YH. Because there is stoichiometry relationship among the reactants and products, the reaction rate should also be related. This leads us to the relationship between stoichiometry and kinetics. We'll spend the next few classes covering the kinetics of the biological processes.